Welcome to IT Pro TV. I'm your host, Don.
Coming at you live from San Francisco, California.
You're watching IT Pro TV.
Hello, and thank you for choosing IT Pro TV, helping you learn wherever you go. I'm your host, Zach Memis, as we continue on with CompTIA and NetPlus. The name of this episode is Wireless Technologies, and we've asked Wes Bryan to come on by and help us out with this. Wes, good to see you again, sir.
Hey, Zach, thanks for having me back. That's right. We're going to be looking at one of the most prevalent communication types in the world right now. Yeah, that's right, wireless, right? It is becoming more and more popular as we speak. I tell you, there are just tons and tons of these devices, millions of these devices out there across the global internet, if you will, on networks, local area networks worldwide. So it is important as a Network Plus technician that you are familiar with some of the standards that we're going to talk about. Now, speaking of standards, we're going to talk about something known as 802.11. Now let's go ahead and step back just a little bit and review a little bit. We've talked about Ethernet standards in other episodes. Remember, Ethernet is an 802.3 standard. Well, what is 802.11? Well, if you don't remember, all right, let's recap. IEEE, the Institute for Electrical and Electronic Engineers, met in February of 1980 to discuss local area network communication technologies and bring some kind of formal standardization to them, right? Remember that standardization gives us interoperability between networks, and that's what we want, because in those early days, everybody was talking about everybody was inventing networking communications, and it wasn't a one-size-fits-all, and everybody was doing things a little bit different, so they decided to standardize them. All right, move forward now from 1980, February, and that's where 802 gets its name from, again, February of 1980. But move forward in time to around the mid-late 90s, and they decided that it was time to start with an 802.11 standard, and that 802.11 standard specifies wireless local area network communications. All right, so when we talk about 802.11, I want you to realize that that is wireless local area network implementations. And there are some variations of it that have, we've gone through different revisions of the standard, new technologies, and one of the things that you'll see, in fact, I got a little list here, is that 802.11 is the overall standard. And after that, what you have is usually this letter that denotes which revision of the standard it is, right? And each revision will bring new technologies, new features, if you will. Sometimes you'll have old features that'll still be there, but as they develop the technology, you'll see that we'll advance and progress with different types of communication features. All right, so what are those 802.11 standards that you have to be aware of for the Network Plus exam? Well, A, B, G, N, and one of the ones that is more current at the time of this episode that we're taping this, 802.11ac, which is one of the newer 802.11 standards. All right. Now, when we look at these standards, A and B, they were released in 1999. Believe it or not, they were released at the same time. The B devices that would be out there were a little bit cheaper when they were implemented, so they became a little bit more prevalent than the A devices, because the A devices were very expensive. All right, so you wouldn't start to see some of those A devices until, about a year later or so. So people think that the B actually came out first when really they were standardized at the same time. In 2003, they came out with the 802.11g standard, and then in 2009, they come out with the 802.11n standard, and then later, I want to say maybe 2013, I believe it was, don't quote me on that one, and I don't think they're going to, if you know it's the newest one, you'll be doing good. They came out with the AC standard, all right? So that's a little bit about the history and timeline of these standards. Now, you might want to know some other characteristics for the exam. One of the things that they call out is frequencies, all right? Now, on your exam objectives, they just say 2.4 gigahertz and 5 gigahertz frequencies. Let's just stop there for a second. 2.4 gigahertz spectrum, that is the ISM band, the Industrial, Scientific, and Medical band. The 5 gigahertz band, if you will, is the UNII band, right? 5 gigahertz spectrum. Now, inside of this spectrum, understand that it's broken up into smaller subcarriers, right? And depending on how we combine those carriers, tells us what our channel bandwidth might be. And we'll look at the channels a little bit later on, all right? But no, those are the two different frequencies that some of these standards are operating in. That is important for the exam. Let's go ahead and let's take, when it comes to frequencies, let's take a look at the top, right? And that'll be the very first specification we look at. And when we look at frequencies, 802.11, you're talking about, or 802.11a, when it was released, operates in the 5 gigahertz spectrum. B devices, they operate in the 2.4 gigahertz spectrum. So you also have to know a little bit about compatibility, right? Because one is operating in the 2.4 gigahertz spectrum, the other one is operating in the 5 gigahertz spectrum, they're not compatible with each other, all right? However, when they came out with the G devices, one of the things that they kind of had the foresight to say, hey, you know what, maybe when we come out with this new standard, we really should make it compatible with one of the ones that was so popular, right? And I don't know if that's their actual thinking, because these are brilliant electrical engineers that designed this stuff. But when they released the 802.11g standard, it also operated in the 2.4 gigahertz spectrum. So, compatibility. One of the great things about the G devices, the G technology and standard when it came out, is that it was backwards compatible with B. Which means that if I brought a brand new network online, the G network online, guess what? If you had existing, which many people did, existing B devices, they could connect no problem, all right? Now, in 2009, when the IEEE ratified or changed the standard, if you will, added to the standard actually, they wanted to make sure that you get improved performance with backwards compatibility on all existing protocols at the time. So when they released the 802.11n standard, what you end up seeing is that it is a dual band technology. That's right, you have radios or antennas, if you will, on it that are operating in the 2.4 gigahertz spectrum as well as the 5 gigahertz spectrum. Now, what does that do for us? Well, if we look at our chart here, you'll see that the 2.4 gigahertz spectrum, that means that N devices are compatible with G and B devices. Well, it's also operating in the 5 gigahertz spectrum. So it means it's also compatible with the A devices. So they achieved their goal. That was their goal, to make sure that we have backwards compatibility with all existing protocols, right? Now, AC devices, they operate in the 5 gigahertz spectrum. Now, that doesn't mean, by the way, and not for the exam, but it doesn't mean that you might not find AC devices that have 2 radios in them that actually operate in the 2.4 gigahertz spectrum as well as 5 gigahertz. I know the one that I got at my house will operate on both. That's not part of the AC standard, though. The AC standard says the 5 gigahertz spectrum. Why is that? Well, the 2.4 gigahertz spectrum is heavily used. It's oversaturated, right? A lot of congestion, a lot of devices use 2.4 gigahertz spectrum. 5 gigahertz spectrum is relatively unused. It'll become more and more popular, you know, and it'll become more and more congested as time goes on. But given the lifespan between these two, 2.4 gigahertz spectrum is very, very heavily used, so it can cause a lot of congestion. So those are some of the things that you have to know about the frequencies and their associated standards, now, or respective standards. The next thing we have to know is, well, speed, transmission speeds. Well, let's go ahead and take a look at that. Across the board, when A devices came out, they were operating at 54 megabit transfer speeds. Now, very expensive technology, but corporate environment could justify the cost, if you will, to get the speeds. Because if you look by comparison of the day, it was 5 times faster, or just under 5 times faster than what the B devices were, operating at 11 megabit transfer speeds. The G devices, one of the things that was really good about the G devices and kind of signaled a death blow for the A devices is that it not only operates in the 2.4 gigahertz spectrum, but as you can see, it also gives you the 54 megabit transfer speeds, all right? So again, very, very good standard, and you can see that they were increasing the performance levels of these technologies. Now, the next one that we have is 802.11n, and 802.11n operates up to 600 megabit transfer speeds. Now, that doesn't mean that in actuality, you know, in practical implementation that you're going to get 600 megabits. It just means that the theoretical upper limit, they got to put a capacity on what it potentially is capable of. It's really related to how many antennas you have in the device, and we'll get back to that because we got to talk about something known as MIMO. No, this isn't a little fish that we're trying to find. This is the multiple in, multiple out. All right, so finding MIMO, not the other one. And we'll get back to that. Now, if we can look at the AC devices, notice that the AC devices up to 1.3 gigabit transfer speeds. Right, we're talking gigabit wireless. Right, 1,300 megabit transfer speeds if you want the other comparison. So you can see that today these wireless networks are pumping a lot of information, and they have to, because high definition is very prevalent today. Streaming media is very prevalent today, and we're having more and more of these devices on wireless networks. So we definitely need the bandwidth and increased bandwidth to make sure that these devices can operate at the performance levels that we're expecting them to operate at. All right, so that is a little bit about speed. Next thing that we have to know that they call out is not only the transmission speed, but the transmission distance. And I've got some basic distances here. I will tell you that sometimes you will see variations, slight variations on these. You might even see them measured in feet versus metric system meters. But I'll go ahead and give these to you in meters, right? So A devices are 100 or 10 meters per range. Understand that that increased speed was great, but it was a really short range. However, the B and the G devices, we're talking about 100 meters, right? 328 feet. When you get to N, you're talking about beyond 200 meters, as same thing with AC devices. However, I will tell you, whether you're indoors or outdoors has a heavy effect on, you know, how far the distance is, right? A lot of manufacturers don't like to quote distances just because there are things that if they do quote you a distance and you don't get that range because of obstacles, because of interference, because of placement of the access point, then you can think that maybe their devices are, you know, subpar performance, when in actuality it's just because there's a lot of things that are hindering the signal. All right, so definitely want you to know those transmission distances. Now, the next thing I also want to talk about briefly is something known as channel bandwidth, all right? See, inside of like 2.4 gigahertz and inside of the 5 gigahertz, you have a range of channels, right? And we'll look more at those channels in a second here. All right, in the earlier days, what you would see is that you would get a 20 megahertz bandwidth, right? 20 megahertz, basically your overall spectrum. How much of that slice would you get basically to communicate between a source and an endpoint, right? In the earlier days, things like your A devices and your B devices and G devices, for that matter, operated at a 20 megahertz bandwidth, right? However, when N devices came out, remember one of the things that I said is that backwards compatibility with all legacy protocols, including increased performance? Well, that's because they found a way that in the N devices, you could take 2 of those 20 megahertz channels. By the way, you're taking all of those channels. You can only have 2 of the 20 megahertz channels, or you can combine them together and you can get a 40 megahertz channel. All right. Now, there is something that I'm also going to, there's a slight caveat to that too that I'm going to come back to as well, because it depends on what kind of mode your wireless router is in, whether it can operate at the 20 or the 40 megahertz. All right. Now, if we can look at the slide here, so not only do we have A, B, G operating all at 20 megahertz, remember N can operate in 20 megahertz, or it can operate in 40 megahertz. All right. If I want backwards compatibility, operate in 20 megahertz, right? 20 megahertz is going to be reserved for the N devices. 20 megahertz is going to be reserved for those earlier devices, right? When AC comes out, check this out. The base minimum bandwidth is 40 megahertz, and then it doubles over there. We can take more, and this is why it operates in the 5 gigahertz spectrum, right? We could have a 40 megahertz bandwidth, or we can combine 2 of those 40 megahertz bandwidths and get 80 megahertz, or what is it, the total of, and I've got some of the totals down here because I can't remember these. You can get 12 40 megahertz, 5 gigahertz channels. You can get 6 of the 80 megahertz, or you can get 2 at 160 megahertz, right? So just basically like channel bonding. You're just putting all of these channels together in one big communication pathway, and it's increasing the overall communication speed that you get. It's one of the great things about doing things like channel bonding, or you might hear it if you're talking about wireless communications, link aggregation, right? NIC teaming, where I take 1 gigabit port and I team it together with another gigabit port. One's for sending and one's for receiving. So essentially what you get is a 2 gigabit communication pathway. Well, that's essentially what channel bonding is. Essentially, when you go from a 20 megahertz bandwidth, take another 20 megahertz bandwidth, and you bond those 2 channels together, now you get a 40 megahertz bandwidth. All right, so it's something that, depending on how they do it, sometimes they do it for redundancy and fault tolerance, but in this case, in wireless, we're going to do it for increased communication speed or increased performance. All right, so those are some of the things that I want you to be aware of when it comes to your bandwidth. Now, the other thing that I want to just kind of go over again is the compatibility, because they might set you in a scenario where you have to find out, is this device compatible with this network? And you have to be aware of that. So if we can review this chart one more time, I want you to keep in mind that A devices, they're only compatible with your N devices, right? My head's kind of covering this up here, but your A devices are only compatible with N devices because of the 5 gigahertz spectrum. However, these 2.4 gigahertz spectrums, right, they're a little different, right? Because the B devices, G and N, all operate in 2.4 gigahertz, they're all compatible with each other, right? And if you have to pause the video to get this down and under your belt, do it. This chart right here I've written down many times before, and it has saved my bacon when it comes to an exam. It is the easiest way that I found to study this. Now, that being said, N is backwards compatible with all of them. The last one, again, my head's kind of covering up here, is the N devices for AC. Because AC is only operating in 5 gigahertz. That does not make it compatible with A devices. It is compatible with N and N only. All right. All right, next thing I want to talk about is what is known as antenna technology. All right. Now, I've mentioned MIMO. Like I said, this is not a little fish that we're trying to find. This is multiple in, multiple out. All right. And what it means in the earlier days is, let's say I was an antenna sending a communication to Zach, okay? It was send the communication and wait to receive the communication. Send the communication and wait to receive the communication on an antenna. Now, what about taking more than one antenna and sending and receiving communications? That's multiple in, multiple out. All right. Now, it uses more than one, like, spatial stream, if you will, for the communication. And it allows us to send and receive, if you will, at the same time, which earlier standards we couldn't do that. Now remember, if we can go back to this chart here, remember one of the things I told you is that with 802.11n, you would get up to 600 megabit transfer speeds theoretically. And I said that that was based on how many antennas you have. Well, here we go with the streams, all right? No, not total protonic reversal. What we're talking about is the N devices would have 4 simultaneous MIMO streams. And every individual stream operated at 150 megabits. If you multiply that times 4, you'll get 600. However, not all your device manufacturers would put 4 streams. One of the streams might be done for, error detection and just control of the communications, where 3 of your antennas might be actually sending and receiving the information. So it's really dependent upon how the manufacturer implements it. Now, if we look here, we've got for 802.11 AC, it supports MIMO and something else called MU-MIMO, or MU-MIMO, if you will. And that's multi-user MIMO, because not only does this have the 4 streams MIMO technologies that N does, remember, it doubles the bandwidth, all right? And that means 8 streams. And that's where we get, again, up to that 1.3 gigabit transfer speeds, all right? That's multi-user, multiple in, multiple out. Easiest way to think of this, ladies and gentlemen, don't let that acronym fool you, right? It just allows you to send and receive communications at the same time, right? And then you also have things like adaptive antenna technologies. Adaptive antenna technologies just means that we can do things like, if the access point supports it, it can do things like beam forming. You could say, oh, Zach, you know what? I can see you're over here in this cell. Let me go ahead and point those antennas adaptively in that direction, right? But that's something I don't believe that you have to worry about for the exam. All right. Now, speaking of antennas, we've got a couple different types of antennas that they want you to be aware of. All right. One of the ones that they want you to be aware of really only does things in a single direction, and that's called a unidirectional antenna. All right. And I got kind of an example of a unidirectional antenna, right? Unidirectional antennas are ones that have a beam, if you will, and it's focused, again, uni, right? One, single direction. Versus an omnidirectional antenna, which kind of, if you would look at a 360 degree, like a 360 degree pattern. And it is important to understand that. Like, for instance, you can take a piece of software to find out, where are my antennas placed right now? What access points do we have around that aren't my access points? And we can do something like a site survey, right? And when we do a site survey, we might want to be finding out, where do I place my antennas, right? Well, I want you to see that if I have a directional antenna, like say for this right here, all right, let me see if I can grab that. There we go. And I put that antenna facing out, well, I'm not really doing much justice for the coverage of that building, right? It might be good for the person that's in the van outside collecting your information, you know, without you knowing about it, but it's not really going to do much for your coverage, right? So in this case, I want you to know that these antennas are directional, and they can be unidirectional or omnidirectional, right? Unidirectional, you might say highly directional as well, all right, because they focus that beam in a certain, in one direction, where omnidirectional, again, radiates it in a 360-degree range, if you will. Understand that antennas, they're measured, their signal strength is measured in gain or decibels, right? You do want to understand that you increase the gain, you increase the signal strength, right? It doesn't mean that you increase signal clarity, it just means you increase the signal strength, right? Anytime you increase power on anything, you also run the risk of having electromagnetic interference or radio frequency interference, right? So definitely know the difference between the unidirectional and the directional antennas. Now, I did mention channels, and I want to go ahead and just take a second and kind of mention wireless channels too. All right, when we look at wireless channels, I've got an example of our 2.4 gigahertz spectrum here. If we take a look at that, you're going to see that we have 11 channels. Now, I know some of you out there probably looked at a map like, or like a document like this, and I know what you're going to say. Wes, I know there are 13 channels. All right, well, there are, but we can't use 13 channels. Here in the States, we're only allowed to use, according to the FCC, 11 channels. 12 and 13, I'm pretty sure, I think it might even be 14 channels now, I think, but they're only used in Europe, and the last one's only used in Japan. It's only one country that uses them all. So you don't have to worry about those extra channels beyond 11 for the Net Plus exam. What you do have to understand is that these channels, right, remember I said they're like subcarriers? You have an overall range of 2.4 gigahertz spectrum, and it more specifically is 2.4112 megahertz all the way up to 2462, 2,462 megahertz, right? But then take this overall range and chop it up into individual subcarriers, these channels, if you will. Now, you're going to notice that I have these color-coded. What's that about? Why do I have them color-coded, right? Well, it's not just making it easier for me, a little bit maybe, but it's also what it's doing is I want you to notice that 3 of these channels are typically what we use here in the States because they're called non-overlapping channels. We can use all of them, 1 through 11, you really can. But a lot of times what you'll see is your wireless access points will default to 1, 6, or 11. Why? There's no overlap. And this is why I color-coded that, right? If you notice that the green channels, 1, 6, and 11, notice that they don't overlap with each other. And that's great, right? We don't get channel overlap, we don't get signal congestion, right? It gives us a better performance. However, if I was to place an access point on, let's say, channel 2, and somebody else is on channel 1, now we could have a performance hindrance, right? Because we are overlapping the channels. So you want to remember what the non-overlapping channels are. Now you can see that inside of the UNII spectrum, the 5 gigahertz spectrum, you start at 5.1 or 5180, 5,180 megahertz all the way up to 5,825 megahertz, and then they divide it from there on out. All right. You don't have to worry, I believe, about the individual channels on here in North America for the 5 gigahertz spectrum. These are the ones according to the FCC. They're also regulated here in the States. All right, let's see. So that's got our channels here. That is definitely something we needed to talk about. I think one of the last things that I want to mention, Zach, before we wrap this one up are just a couple of the cellular technologies that they want you to just kind of to be aware of. And they call out a few. Some of them maybe you've seen, maybe you haven't heard of them. And there are other ones out there, by the way, too, ladies and gentlemen. But the 3 cellular technologies that they call out are GSM, TDMA, and CDMA. All right, so what are these about? Just more alphabet soup to throw your way. Let's see if we can hand you a fork and teach you how to eat it. Global Systems for Mobile Communication. It is one of the most popular, highly distributed cellular communications worldwide. I think there's like 210 plus countries that use it, right? TDMA, all right? This is called time divisional multiple access. And when we talk about TDMA, I want you to understand that what it does is it takes your radio, like we were talking about those channels and stuff, it takes your radio frequency and it divides those channels into discrete time slots, all right? And then those time slots are allocated to the people that are using the communication channel, right? So I could say for something like this, I could say, okay, Zach, it's your time to talk. Okay, Zach, it's not your time to talk. Wes, it's your time to talk. You can use the communication. And we keep rotating through those time slots. This is a way you can use a single finite domain, and we can use multiple channels, multiple communications can use those channels and rotate through the channels all within that same fixed bandwidth, right? I can tell you, Zach, it's your turn to talk. I can tell the next person, now it's their turn to talk. And again, we keep rotating through those channels, right? So that's time divisional multiplexing. The other one is CDMA, and CDMA is interesting, all right? It uses what's known as spread spectrum technologies as well. Again, spreading that information, those communications, if you will, amongst all those different channels. But it does it a little bit different, right? It doesn't use time slots, right? Like time divisional multiplexing does. This uses codes. And a code I want you to think of as a language, all right? The sender and receiver, they have to be speaking the same language in order to understand the communication. So if I assign a code to Zach and I assign the same code to myself, and again, it's the underlying technology, I'm not going to do anything here, right? It's built into the technology, then Zach and I can communicate within that spectrum, right? If somebody else, and I'll give you an example, right? I love Mexican food, absolutely love me some guacamole now, let me tell you. But if I'm sitting down at a restaurant and we have a family that's sitting next to me, and I wish I could speak Spanish, I still want to learn a beautiful language, but I don't speak Spanish, right? So if they're sitting next to me, and let's say they were trying to have and they're communicating, right? They're speaking in a different language. It's not meant for me. And because I don't know the language, I can't partake in that communication, right? That's what a code is, all right? So when we say code divisional multiple access, your codes have to match from the sender or receiver, all right? And we can use multiple codes within that bandwidth, right? And spread those different communication channels based on the codes, provide the sender or receiver have the same code. That's code divisional multiple access. I'm just going to throw one out here for you guys and gals because I don't like leaving this one this way because there's another one there, and that's something known as frequency, FDMA, frequency divisional multiple access. I said multiplexing. Let me back up here. Time divisional multiple access. That's the A part. There is no I don't know why I said multiplexing. Yeah, multiplexing in general says, hey, how can I take more than one signal and combine it over the same medium? Again, with time divisional multiple access, it's discrete time slots. Code divisional multiple access, it's codes, languages. If you think about them, codes are languages, right? It's the best way I can think of to explain it. You don't understand the language, you're not a part of the communication. You don't have the code, you're not a part of that communication. But the last one I do want to kind of mention, even though it's not in the exam objectives, and that's FDMA, frequency division multiple access, all right? So if I have one person, in fact, let's go back to my diagram, right? Let's say we got all these different individual frequencies. It means I can have somebody, it's also called frequency hopping spread spectrum. And this means that the transmitter and the receiver have to know beforehand, just like codes, just like time slots. They have to know what the frequency is as they're going to change. This goes all the way back to the late 1800s. And this would be where, let's say that Zach and I are communicating at this point, we're communicating on channel 1 at 400 or 2,412 megahertz. He has to be on 4,1200 megahertz as well. But then we jump up, all right? And we jump up. Now we're operating on 2,417 megahertz. And we hop through the spectrum. That means once we hop to 2, or we hop to 3, or in this case, non-overlapping channels, I go from 1 and I go to 6, well, that means somebody else can use 1, right? Why can they use 1? I'm not using it anymore. And we can keep hopping through the different channels, and that's how you can have multiple independent communications within the same domain like that, because you're hopping through the different channels. All right, so those are some of the things and some of the technologies that we want you to be aware of when it comes to the exam. Remember, I know it's a lot of standards. I know it's a lot of specifications, but if you can get these under your belts now, you're going to be doing great for the next Network Plus exam.
And you're very fortunate because this is a video that you can watch again and again and again when it's finally mounted to our course library. So this has been Wireless Technologies, great episode. In fact, in the CompTIA Net Plus series, watch them all. They're all fantastic. Wes does a great job. And in that course library, you're going to find hundreds of other videos. They're all created for one purpose, to help you go further. And thank you for watching IT Pro TV. Tell everybody you know about IT Pro TV. They'll be glad you did. I'm Zach Memis.
And I'm Wes Bryan.
And we will see you soon.
Thank you for watching IT Pro TV.